Until now, no one has ever succeeded in explaining the quantum mechanical correlation in Bell test experiments. Bell made a valiant attempt, but he also didn't succeed. At the end of this video, we shall see why he didn't. The following explanation is based on the assumption that quanta have definite properties. Based on the idea of entanglement, Einstein, Podolsky and Rosen already demonstrated in their famous article from 1935 that quanta should have definite properties. However, the Copenhagen interpretation disciples, following Bohr, assume quanta to be in an indefinite state until they interact or are being measured. In the following model for the explanation of the quantum mechanical correlation, I will decisively answer the question which one of these conceptions is the right one. In Bell test experiments, sometimes the spin of entangled electrons is measured to determine the correlation. Entangled electrons are in fact electron-positron pairs. Although spin of entangled electrons is always opposite, yet detectors can give a result of equal spin when they are not adjusted in the same direction. The relation between the difference in angle between the detectors and the number of cases of equal spin is called correlation. Correlation is defined as the difference between the number of cases of equal spin and the number of cases of opposite spin, as part of the total number of measurements. Spin of electrons is a vector in an arbitrary direction. Spin of entangled electrons is exactly the opposite. A detector is considered to be a plane consisting of parallel lines, the detection lines. The position of this plane is perpendicular to the line of motion of the electrons. The direction of the detection lines is the direction in which the detector is adjusted. The detector is provided with an imaginary perpendicular plane which divides the detector in an upper half and a lower half. Spin is measured by projecting the spin vectors in the direction of the line of motion of the electrons onto the detector plane. When a vector lands on the upper half, its component in the detecting directions point upwards, and this vector is detected as up. And when a vector lands on the lower half, its component in the detecting direction points downwards, and this vector is detected as down. In Bell test experiments, everything takes place on one line. The electrons move in opposite directions along this line. The detectors are positioned perpendicularly with their centers on this line. These experiments are aimed at detecting directions. For directions, it doesn't matter where they start from. So, for a better visualization and to make things more comprehensible, we can move everything, including the detectors, to one point on that line. By doing so, the experiment takes place at one point on the line of motion. That point is called C. Also, the entangled electron pairs are produced at that point and stay there. Assuming spin vectors to have more or less the same length, and because of the fact that in Bell test experiments many electron pairs are detected with spin in random but opposite directions, their spin vectors will form a sphere with its center in C. The center of the detectors is also in C, and the detectors are placed perpendicularly to the line of motion of the electrons. Detector A is adjusted in a vertical position, and during the whole experiment it will stay in that direction. Detector B is adjusted at an angle of phi degrees in relation to the vertical. In this way, the central perpendicular planes of the detectors will divide the sphere of spin vectors into segments. There are two segments between the central perpendicular planes, which we will call space 1 and space 2, and two remaining vector spaces, which we will call rest spaces. It is obvious that spin vectors of an entangled pair are either both in spaces 1 and 2, or they are both in the rest spaces. Otherwise, they are not opposite. When we now look at opposite spin vectors in spaces 1 and 2, we will see that both vectors are situated in the same hemisphere of the detectors. If vector 1 is in space 1 and being measured by A, then that vector is, for example, in the upper hemisphere of A and is detected as up. That means that vector 2 in space 2 is in the upper hemisphere of B and also detected as up. If vector 1 is in space 2 and being measured by A, then that vector is in the lower hemisphere of A and is detected as down. Then vector 2 in space 1 is in the lower hemisphere of B and is also detected as down. So we see that opposite spin vectors in the spaces 1 and 2 give equal spin results. In the same way, we can see that opposite spin vectors in the rest spaces give opposite spin results. In a Bell test experiment, spin is measured of many pairs of entangled electrons. The opposite spin of all those pairs will be spread evenly on the sphere. Therefore, defining the correlation boils down to the measurement of the various projected vector spaces on the detector planes. Now, there should be a relation between the correlation and the size of the vector spaces. However, according to quantum mechanics, correlation is proportional to cosine phi, but the size of the vector spaces is proportional to phi. Also, the projection of the vector spaces on the detector planes is proportional to phi. The conclusion must be that these vector spaces are not the correct spaces. But when spaces 1 and 2 are rotated 90 degrees around one of the detection directions, their projection on the detector planes is indeed proportional to cosine phi. We will call these rotated spaces space 1, 1 and space 2, 2. To understand why the projection of these spaces is proportional to cosine phi, we can look at the cross-section of the sphere in a vertical direction and in the direction of the line of motion. This is a parallel circle, perpendicular to the detector plane. The intersecting line of this circle with the detector plane of A is the diameter of the circle and at the same time a detection line of A. The projection of the points of the circumference onto the diameter, also the detection line, is given by cosine squared, alpha divided by 2. The diagram of this looks like this. This also goes for every detection line and so for the whole of the detector plane. The part of the detection line covered by the projected spaces 1, 1 and 2, 2 is exactly equal for all detection lines. This is certainly not the case for the spaces 1 and 2. That covered part is being measured by all the detection lines against a scale of cosine squared, alpha divided by 2, in which alpha divided by 2 is equal to phi divided by 2, plus or minus 90 degrees. This is because the pointer of alpha starts at the top of the diameter detection line. But the central perpendicular plane of B, however, indicating phi, starts in the middle of the diameter or detection lines. So phi is equal to alpha minus or plus 180 degrees. So the size of the projected spaces 1, 1 and 2, 2 is proportional to 1 minus cosine squared phi divided by 2. This process of projection to explain the cosine does not only go for the vertical direction, but for all directions a detector can be adjusted in. rotating around the line of motion of the electrons. So the process also goes for detector B, no matter at what angle it is adjusted. We now project the spaces 1, 1 and 2, 2 onto the detector plane and vary phi from 0 degrees to 360 degrees. The size of the projections can be represented in diagram. This is the diagram of 1 minus cosine squared, phi divided by 2. The size of the projection of the rest spaces is then 1 minus cosine squared, phi divided by 2. And this is cosine squared, phi divided by 2. The correlation then is 1 minus 2 cosine squared, phi divided by 2. And this is minus cosine phi. So the spaces 1, 1 and 2, 2, the 90 degrees rotated spaces 1 and 2 are indeed the correct vector spaces. But why should spaces 1 and 2 be rotated 90 degrees? The answer to this question is as surprising as it is simple. It is because of perspective. Perspective is the direction in which the universe is observed. Fundamental theories on physics, such as quantum mechanics, describe the universe from one perspective. In Bell test experiments, the universe, consisting of an entangled pair of electrons with opposite spin, is observed by the detectors from two perspectives at the same time. To make the results of the experiments fit in with the result of the theory, all perspectives of both detectors in relation to each other as well as the perspectives of the detectors in relation to the perspectives of the electrons must be made to correspond with each other. This can be done by carefully taking into account all rotations, right from the start. Bell test experiments, therefore, don't start with the detection of spin, but with the positioning of the detectors. The fact that the detectors are placed perpendicular to the line of motion from a fixed position in space is essential in the explanation of the correlation. The sequence in which the rotations are taken into account makes no difference. Translation has no effect on perspective at all. For a better understanding of the phenomenon of perspective, we can look at an example in our everyday world. Two observers, A and B, are standing in front of a glass door with a handle on the right-hand side. On the door an arrow is drawn, pointing at the handle. A and B both see the arrow pointing to the right. A asks B to go to the other side of the door and tell which direction the arrow is pointing. B goes to the other side and turns around 180 degrees. He sees the arrow pointing to the left, so now the answers of A and B don't correspond any longer. To make them correspond, it is enough to make the observed universe, in this case the glass door, move the same way that B has done. When the door has rotated 180 degrees, B sees the arrow pointing to the right again. It is obvious that B now observes the universe from the perspective of A, because now the situation is relatively the same as if B and the universe had not moved at all, but A moved in the opposite way. In this way, rotations can be taken into account and perspectives can be made to correspond. There is another way to achieve this, by not letting the observers to refer to themselves, but to the observed. Their answers would also correspond. If A is in front of the door and B is behind it, they will both say the arrow is pointing at the handle. Returning to Bell test experiments, one can wonder from which position the detectors are to be placed perpendicularly to the line of motion if this isn't done at random. The line of motion of the electrons is a given. When the direction of detection of the detectors is chosen to be vertical, then with this a second direction is defined. These two directions together define a plane in space. In this plane, the detector planes must be placed. But the line of motion of the electrons is also in that plane, so to get the detectors perpendicularly to the line of motion, they must rotate 90 degrees. This is the reason why the vector spaces 1, 1 and 2, 2 are the correct spaces. Not because the spaces 1 and 2 had to be rotated 90 degrees, but because both detectors have already been rotated 90 degrees with respect to the line of motion while being perpendicularly positioned. Because the line of motion is also the direction in which the spin vectors are projected onto the detector planes, the detectors have also been rotated 90 degrees with respect to the vector spaces 1, 1 and 2, 2, while being perpendicularly positioned. While positioning the detectors, the spaces 1, 1 and 2, 2 stay where they are with respect to the electrons, whereas the spaces 1 and 2 move together with the detectors. The spaces 1, 1 and 2, 2 and the spaces 1 and 2 are all equal spaces between the central perpendicular planes as soon as B has been adjusted. They are equal concerning shape and size, not concerning position. The perpendicular positioning of the detectors manifests itself in defining the position of the correct vector spaces. The adjusting of detector B manifests itself in the size of the vector spaces and, by measuring their projection, also in the correlation. In order to measure the vector spaces 1, 1 and 2, 2, the perspective of B must be made to correspond with the perspective of A. When A and B start in the same position, B has to undergo 2 rotations when adjusted. 1 rotation of 180 degrees and 1 rotation of 5 degrees. Now suppose A measures space 1, 1 and B measures space 2, 2. Then how does B perceive space 2, 2 from the perspective of A? As we have seen from the example of the glass door, it is enough to make space 2, 2 move the same way that B did. That is, like this. This shows that B measures space 2, 2 in the same way that A measures space 1, 1. Of course, in reality, space 2, 2 doesn't move the same way that B did, but if A and B are made to refer to the spaces 1, 1 and 2, 2 themselves, then it is also clear that A and B perceive the spaces 1, 1 and 2, 2 as having the same size, because the spaces 1, 1 and 2, 2 are symmetrical in respect of C. As we have seen in the explanation of cosine, it makes no difference to the projection at what angle the detector is adjusted. The projections of the vector spaces 1, 1 and 2, 2 on the detector planes are identical in shape and size. That means that the direction of the detector makes no difference in the measuring process of a projected vector space on the detector plane. And that means that it is not necessary to make the perspectives of B correspond to the perspective of A. It can be done, but it makes no difference. For that reason, A and B, perceiving the electrons with their opposite spin from 2 different perspectives, give results that accord with the results given by quantum mechanics from one perspective, the perspective of the electrons. It is, however, essential to make the perspectives of the detectors correspond to the perspectives of the electrons for the identification of the vector spaces, to define their place in space. The size of the vector spaces is defined by the angle phi between the detectors, because phi is also the angle between the central perpendicular planes of the detectors. Based on the assumption of definite properties of quanta and the correct application of perspective and projection, it has been demonstrated that the correlation solely depends on the position of the detectors, and so just depends on phi, as indeed the formula for correlation shows. The combination of detector adjustments determines the combination of spin results. equal or opposite, and the ratio between them. There is no spooky action at a distance, no instantaneous information exchange between electrons of an entangled pair is needed to explain the correlation. So the explanation in this model is completely consistent with local realism. Bell assumed that when being measured at various angles, electrons choose their spin at random. This is also the viewpoint of the Copenhagen interpretation followers. But because of this assumption, Bell's theorem is not applicable to spin measurements of entangled electrons. This is because projection doesn't make a difference in the case of indefinite spin. The chance for two arbitrary spin vectors to be situated in the vector spaces 1, 1 and 2, 2 is again proportional to phi, not proportional to the cosine of phi. Yet projection is needed to explain the correlation. When, however, a fixed opposite spin is assumed, the correlation is perfectly explicable, because then the spin vectors are situated in vector spaces which, projected onto the detector planes, account for the cosine in the formula of the correlation. When calculating the probabilities of this theorem, Bell also added a factor lambda to take into account possible hidden variables. He thought with this factor to have covered all possibilities to explain the correlation. However, a random, indefinite spin can never become a fixed, opposite spin, whatever the factor lambda might be. So, by assuming an indefinite spin, Bell closed one road to explain correlation, the road of a fixed, opposite spin. Einstein's viewpoint. This model has shown that it is exactly this road that has been leading to an explanation of the quantum mechanic correlation. Einstein was right again.